Today we are going to start with the next chapter, that is the wave optics. Okay, so let's begin. So now Huygens was a scientist who gave us wave theory of light, and before that Newton gave us corpuscular theory of light. It could explain certain phenomena like rectilinear propagation of light. Just like particles travel, corpuscle means particle, just like particles travels in a straight line, so light also travels in a straight line. Newton's theory could explain that. Then he explained reflection and refraction of light, etc. So certain phenomena he could explain. Then came Huygens, and he gave us the wave theory of light. Okay, so now Huygens theory could explain more phenomenon compared to that of Newton's theory, but people believed in Newton. Okay, so nobody looked at Huygens theory for 100 years or so. Okay, because Newton was a great figure in science, so everybody believed in Newton and nobody believed in Huygens. Okay, and then certain experiments came which could be only explained using the wave nature of light, and that's why we are studying now the Huygens theory. Okay, so light is made up of waves. Okay, and light is made up of what? Electromagnetic waves. It was proved much later by Michael Faraday and Maxwell in the 18th century, right? Okay, so let's come to the Huygens theory. Huygens says that light is made up of waves. Okay, and a light source sends waves in all directions in a medium. Then the points of medium where light waves reach in phase form a wavefront. Then next, every point on the wavefront behaves like a secondary source of light and emits secondary wavelets which travel in a medium with the speed of light. So Huygens says that every point on the wavefront, it behaves like a secondary source of light. Suppose you take this wavefront. Okay, so all points here, they are in the same phase. So he says that every point on this wavefront, it will behave like a secondary source of light. So suppose this is a point source, then now if you collect all points which are at the same phase, okay, that means these points must be at the same distance away from this point source, then only they will be in the same phase, because same number of waves would be formed to reach at those points. So if this is a point source, the wavefront produced by it would be a spherical wavefront, but then the wavefront would travel only in the forward direction, it will not travel in backwards direction. Okay, so then suppose you take these secondary wavelets, okay, or secondary wavefronts you can say, formed by these sources, and you draw tangent to all of them, then you get another wavefront at some time, let's say time equals to delta t. So in time equals to delta t, suppose these wavefronts, they travel this much of distance, then if you draw a tangent to them, all of them, okay, then you get a next wavefront. This thing is clear? Yes, no? All right, so now there is a question. See, what would be the angle between direction of propagation and the wavefront? What would be the angle between direction of propagation of light and the wavefront? Yes, tell me. This is the direction of propagation of light and this is the wavefront. So what's the angle between them? It's 90 degrees. Okay, this thing is clear? Yes, no? Right, okay. So then another question. Now suppose you have a spherical wavefront. Okay, what is the source of a spherical wavefront? Is it a point source? Is it a line source? Line source means a straight line, okay, or something else? So if you have point source, then yeah, it's a point source, right? A point source, it will produce a spherical wavefront, right? Because if you take a point source, then see, consider wave starting from this source, and if you collect the all points which are at the same distance from this point source, then what will you get? You will get a sphere, right? So then all those points would be in the same phase. Okay, that means okay, if you collect all those points which are in same phase, that means they have traveled same distance from the source, then they are in same they are in same phase. Okay, so that collection of those points is known as wavefront. So point source produces what? A spherical wavefront, right? This is simple. Okay, then next is, suppose you have a cylindrical wavefront like this. What would be the source of this? You have a cylindrical wavefront. What would be the source of? Yeah, a straight line. Okay, okay, it will be produced by a line source, right? Then if you have a plane wavefront, what would be source of this one? You have plane wavefront. Yeah, so it is a point source at infinity, right? If you have plane wavefront, then its source is point source at infinity. Okay, so because see, a point source will produce a spherical wavefront, and then if you consider a big sphere, okay, if you consider a big sphere, then suppose this is a sphere. What, suppose it's a sphere, right? So if you take small part of this, if you take small part of the sphere, okay, small portion, then it looks like a plane, right? If I zoom it, then if I take very small part of this one, then it looks like what? It looks like a plane, flat plane. Okay, just like earth is spherical, no? So if you consider a small portion of earth, it looks like what? A flat surface, right? Okay, so what is the source of plane wavefront? It is point source at infinity. Okay, it is a point source at infinity. This thing is clear. Next, let us see superposition of light waves. Okay, so now superposition of waves is superposition of waves. It doesn't matter whether these waves are sound waves, okay, light waves, etc. See, they will follow same principle. So suppose this is first light wave, okay, it's coming at some point of the medium. So equation of a wave is given by what? Y is equal to a sine of omega t minus kx. Equation of a wave traveling in positive x direction. So for simplicity, let's take x equal to 0. Okay, then you get simple equation, y is equal to a sine of omega t. Second one, this is the first wave. Then you have second wave, whose equation is given by a to sine of omega t plus phi. Their amplitudes are different. Okay, their amplitudes are a1 and a2. Then what would be the resultant amplitude? So we have studied this in waves, okay, only in last chapter. That resultant amplitude would be just equal to what? Square root of a1 square plus a2 square, okay, amplitude of first wave square plus amplitude of second wave square plus 2 times a1 a2 multiplied by cos of phi. Okay, phi is the phase difference between the two waves, right? Then what would be the resultant intensity? So we have also studied this, that intensity is directly proportional to the amplitude square. So I1 would be equal to what? Some constant c times a1 square. I2 is some constant, actually same constant, c times a2 square. Okay, so then this a1 square, we can write it as, see, resultant intensity would be what? The constant c times r square. okay, which can be written as C times R square would be A1 square plus A2 square, okay, plus 2 times A1 A2 cos of phi, right? So the resultant intensity is I1 plus I2, because C times A1 square is I1, C times A2 square is I2, plus you have 2 times A1 A2, which can be written as what? Square root of, okay, I1 I2, okay, because A1 would be what? Square root of A1 square. So you write it that way and you get this formula. The resultant intensity is I1 plus I2 plus 2 times of square root I1 I2 multiplied by cos of phi. Okay. So then you have constructive interference or destructive interference. Now what does it mean? So constructive interference means, we have studied this, that crust of first wave falls on the crust of second wave. Okay, that means crust of first wave will fall on crust of second wave, trough of first one will fall on trough of second one. So the displacements of two get added up, okay, in positive manner, and therefore what happens? There is a big displacement, okay. And for this to happen, so crust of first one falls on crust of second wave, trough of first falls on the trough of second. So for that, the phase difference between these two should be either 0, right, or 2 pi, because crust falls on crust means, so phase here should be equal to phase over here. So phase difference between two must be either 0 or 2 pi, you can say, or 4 pi, so on and so forth. So for constructive interference, the phase difference is integral multiple of pi. Okay, it is integral multiple of, sorry, 2 pi. Okay, integral multiple of 2 pi. So n is equal to 0, 1, so on and so forth. Okay, phase difference would be equal to what? 2n times pi. Okay, and therefore if it is 2n times pi, then cos of 2 pi is equal to plus 1. Okay, cos 0, cos of 2 pi or cos of 4 pi, it is equal to plus 1, and therefore what would be the resultant amplitude? It would be square root of a1 square plus a2 square plus 2 a1 a2. Okay, and what about the intensity? The resultant intensity would be maximum, and that is equal to I1 plus I2 plus 2 times square root of I1 I2. Okay, so we need to remember these formulas, and we had seen them in the waves also. Okay, so this is for the constructive interference. Next is, what's the condition for destructive interference? So here the phase difference would be equal to pi, 3 pi, 5 pi, that means odd multiples of pi. Okay, for constructive, the phase difference is multiples of 2 pi, right, integer multiples of 2 pi, and for destructive it is odd multiples of pi, right. So it can be written as 2n plus 1 times pi, and the values of n are 0, 1, 2, 3, so on and so forth. Okay, integer. Then what happens to the amplitude and the intensity? So the resultant amplitude would be equal to what? Square root of a1 square plus a2 square minus 2 a1 a2. Okay, and resultant intensity is equal to I1 plus I2 minus 2 times of root of I1 I2. Just this plus sign will become minus. Okay, and what does it mean? It means that crust of first one falls on the trough of second one. So if their amplitudes are equal, what will happen? This is positive displacement, this is negative displacement, then the total displacement would be equal to 0, right? If amplitudes are not same, okay, so crust of first one falls on the trough of second one. So this is positive displacement, this is negative displacement. If their amplitudes are same, then what would happen? This displacement plus this displacement would give us what? 0. Okay, also this displacement, this is negative, this is positive. If amplitudes are equal and crust falls on trough or trough falls on crust, then resultant wave would be what? There will be no wave. Okay, so we'll get 0 displacement. But if amplitudes are different, one is big, other one is small, suppose, then what will happen? So for destructive interference, if amplitudes are different, so some displacement would be left, which would be difference between this one and this one, right? So the resultant amplitude is given by this thing, square root of a1 square plus a2 square minus 2a1 a2, and resultant intensity is given by I1 plus I2 minus 2 root of I1 I2. If I1 is equal to I2, then this thing and this thing will be equal to what? 0. Okay, right? So then resultant intensity. So when I1 is equal to I2 is equal to I. Okay, when I1 is equal to I2 is equal to I. Just put that over here. What do we get? I1 plus I2 means it is I plus I, 2I plus 2 times of this is I times I means I square. Take square root of that, you will get I. So 2I cos phi. Okay, and that is equal to, you can take 2 common or 2I common. So we have 2I times 1 plus cos phi. Okay, and if phi is equal to what? 2 pi, then this is 1. So the resultant intensity is 4I, and if phi is equal to pi, right, pi, 3 pi, 5 pi, then this will be cos phi will be minus 1, and resultant intensity would be equal to what? 0. Okay, so this is known as a maxima, where the intensity is maximum. This point is known as what? This is known as maxima, and the intensity, or the point where intensity is 0, it is known as minima. Okay, intensity is either 0 or minimum, that is known as minima, right? This thing is clear. Then there are a few definitions. First is coherent sources. Now what are coherent sources? So two sources are said to be coherent if there is a constant phase difference between them. Okay, so phase difference can be anything. It can be 0, it can be pi, 2 pi, okay, pi by 2, anything. But it should remain constant over the time. It should not change. So those sources are known as coherent sources. Okay, and we'll talk about the interference pattern. So only coherent sources can form an interference pattern. Okay, and monochromatic sources means, monochromatic light means light having only one wavelength. One wavelength means one color. So different colors of light are because of different wavelengths. Okay, and monochromatic means what? Light having only one wavelength means one color, right? Okay, this is clear. Chrome means color, right? Chrome means color. Okay, so monochrome means single color. Okay, so these are some definitions that we need to remember. Now next, let's talk about an experiment called as Young's double slit experiment. So this was the experiment, okay, which proved the Huygens theory, that Huygens theory was correct. Okay, so let's talk about it. So suppose you have, this is a plane wavefront, okay, and then there is a small slit, small opening over here in this cardboard, and in front of this cardboard you put another cardboard at certain distance. So there are two small openings like this, two small cuts, you can call them slits. Okay, so two slits, therefore it is called as double slit experiment. And after some distance, what you do is you keep a screen, a black screen. Okay, so see here, there is some monochromatic light. It's not our white light, that means it's not the sunlight, because how many colors are there in sunlight? There are several colors, right? Okay, at least 7 colors, and then on top of that there are ultraviolet waves. Okay, kind of, it's a mixture. Okay, so you have light of only one color, it's a monochromatic light, right? And see, this we know from the Huygens theory that suppose this is a wavefront, then each point on the wavefront behaves like what? Secondary source. So now if this light strikes on this first cardboard, okay, so wherever you have slit, okay, so all these points on the slit, they will behave like what? secondary sources of light. Okay, so if you consider only point source like this, then they will send secondary wavelets like this. Okay, they will send secondary wavelets like this. Okay, and these two slits, they are at the same distance, they are symmetrically arranged with respect to the first one. So the light will reach in the same phase at S1 and S2. Okay, and again you can say that these two will behave like secondary sources of light and they will send secondary waves in forward direction. Okay, so then what happens, the secondary waves due to the first source and second source, they will travel. Okay, they will travel in the forward direction, and suppose they arrive at some point on the screen, then see there would be waves due to this first source. Okay, these are wavelets, right? These are not waves, these are what? Collection of points in the same phase. Okay, and these are secondary waves due to the second source. Then what happens, they will interfere with each other and bright and dark fringes would be found, will be formed, and this pattern of bright and dark fringes, okay, it is known as the interference pattern, right? This is known as interference pattern. Okay, so see, actually what will happen, so they will produce wavelets, but if you think about any point on the wavelet, it will have some phase. Okay, how will you determine its phase? So you can think of waves coming from the first source and waves coming from the second source. Okay, just consider a single wave. What is a wavelet? It's collection of phases due to n number of waves, right? So just consider a single wave from first source and a single wave from the second source, and then consider some point on the screen. Okay, so this arrangement is shown over here symbolically, right? So this is your first source, that means source of light is somewhere. Then this is your S0. S0 is the first slit. Okay, S1 and S2 are these two slits. The separation between them is small d. Okay, can you see that, or it's very small? Separation between these two is small d. Okay, separation of the screen from these sources is equal to capital D. Okay, and this one is the midpoint of S1 and S2. Then now a wave will start from S1, a wave starts from S2, and these two, suppose they arrive at point P on the screen. Now whether this point will be bright point or dark point, that we need to find out. So we know that point will be bright if the phase difference in the waves coming from S1 and from S2 is equal to what? Either it is 0 or phase difference is 2 pi, right, or it is 4 pi, then the point would be bright. If the phase difference is pi, 3 pi, okay, odd multiples of pi, then it would be dark, right? That we know. So if you think about this point, okay, exactly opposite to the midpoint of S1 and S2, then this is called as center of the screen. So this central point will be always bright. Okay, central point would be always bright. Why? Because the distance covered by this wave traveling from S1 and distance covered by the wave traveling from S2 would be same. S1 and S2 are in the same phase. They are emitting light in the same phase, okay, at a particular time, at any given time, and then light starting from S1 and S2 also travels the same distance. Okay, what does it mean? That light starting from S1 and S2 covers same distance, there is no path difference, that means there is no phase difference while reaching this point, and therefore the point would be bright. No phase difference means crust will fall on crust, drop will fall on drop. So this point would be bright. This thing is clear? Okay, yes, no? Right. So central point would be always bright. Then you consider the difference in path between the wave starting from S1 and S2 to reach any other point, let's say this point P. So what would be the difference? So for that you draw perpendicular from here. So this much is the difference in path, right? This much is difference in path. So it is S2P minus S1P, okay? S2P minus S1P, and we can find it out that this path difference would be, it would be equal to x times small d by capital D. Okay, so what is x? So x is equal to the distance of this point P from center of the screen. Okay, it is x. What is small d? Separation between these two sources. What is capital D? Capital D is separation between sources and the screen, right? So the path difference is equal to what? X times small d upon capital D. Okay. So now if this path difference is equal to 0, or if it is equal to lambda, 2 times lambda, then there would be constructive interference and this point would be bright. Okay. So suppose there is nth bright fringe formed at this point. So central bright fringe, it is known as 0th bright fringe. Then for the central bright fringe, the path difference is 0. For the first one, the path difference would be lambda. For second one, path difference would be 2 lambda. For nth bright fringe on the screen, the path difference would be equal to what? N times lambda, right? So this path difference, x times d by capital D, is equal to what? N times lambda. Okay, and therefore what would be distance of that point? Distance of that point from the center of the screen is equal to n times lambda capital D by small d. Okay, so distance of nth bright fringe, or it is also called as band. Okay, nth bright fringe or nth bright band from the center, that distance is equal to n times lambda capital D divided by small d. Okay, and if you think about dark fringes, then first dark fringe would be formed at the path difference equal to what? Path difference equal to lambda by 2. That means x times small d by capital D equals to lambda by 2. Second one would be formed at 3 lambda by 2. Next one would be formed at 5 lambda by 2, so on and so forth. So how can we write that? So nth dark fringe would be formed at 2n minus 1 lambda by 2, where the values of n go from 1, 2, 3, so on and so forth, right? So then put n equals to 1, you get 2 minus 1, that means 1 lambda by 2. Put n equals to 2, second dark fringe, you get 4 minus 1, that's 3 lambda by 2, so on and so forth, right? So then you can find out x. So what is x? Distance of the nth dark fringe. So just take d and d on other side, capital D and small d. So you get x is equal to 2n minus 1 lambda capital D divided by 2d. Okay, 2n minus 1 lambda capital D divided by 2d. This thing is clear. Then let's come to the next point, that is the fringe width. Okay, what is fringe width? It is distance between two bright fringes or two dark fringes. Okay, and you can very easily check that it comes out to be equal to, see, if you think about bright fringes, so first bright fringe would be formed at what? X1 is lambda capital D by small d. Second one would be formed where n is equal to 2, so it is 2 times lambda capital D by small d. Okay, first one is formed at lambda capital D by small d, second one 2 times lambda capital D by small d. What is separation between them? Separation between them is lambda capital D by small d. So how much is the fringe width? Fringe width is lambda capital D by small d. Okay, so it is separation between two bright fringes or two dark fringes, right? For dark fringes also it will come out to be equal. Okay, so this is the fringe width. Then suppose this is a fringe, so angle made by that fringe, angle made by one band at the position of the sources, it is known as the angular fringe width. Okay, it's known as angular fringe width. So see here, if you just draw a straight line from here, so suppose this is your fringe, if you just draw perpendicular from here, suppose it meets at this point, okay, on the plane containing two sources, and then you connect this point to other end of the fringe. Okay, this is another end of the fringe, this is your fringe. So then if you find tan of this angle, it would be equal to this opposite side divided by adjacent side. Okay, so beta divided by what is the distance between these two? It's equal to capital D. So beta divided by D. Then we know that for very small angles, and the width of these fringes would be very small, it would be a few millimeters or so. So for very small angles, we know that theta is equal to what? It's nearly equal to tan theta, or tan theta is nearly equal to theta, right, for small angles. So otherwise sin theta is less than or equal to theta, it's less than or equal to what? Tan of theta, right? For large angles, sin theta is less than theta, it's less than tan theta. But if angle is very small, all three are almost equal. Okay, so then you have theta nearly equal to what? Beta by D. Theta is nearly equal to beta by D. And so if you take this D on this side, what will you get? So theta is equal to beta by D means it is lambda by small d only. Okay, lambda divided by small d. Okay, this thing is clear. Right? Yes, no? Okay, good. And then next is shift in interference pattern. So now suppose you change the medium. Okay, you change the medium. Then what will happen? Okay, so suppose there is some water, you take this apparatus and drop it in water. Then which of these things would change? Will D change? D will not change. Will the capital D change? It will not change. Will the lambda change? Lambda will change, right? Yes, wavelength will change. Okay, so wavelength is different in different medium. Okay, and that's why then the distance of these fringes from the center and also the fringe width will change if you change the medium, right? So there have been questions like that. Okay, so suppose complete apparatus is dropped in water, what would be the fringe width? Earlier the fringe width, suppose x, what is the fringe width then? Okay, and very few times, but there have been a question like this also. So suppose you have these two sources, no, S1 and S2, and in front of one of these sources, suppose what you do, you put a glass slab. Okay, glass slab, mica slab, okay, some transparent kind of material. Okay, you put slab of that material in front of either S1 or S2. Then what will happen? So see, the optical path traveled in air and optical path traveled in this medium would be different. Why? Because wavelength of the light is different in different media. Okay, so now there would be an extra path difference due to the sheet. Okay, mica sheet, or suppose there is a thin glass sheet, okay, having thickness equal to T, how much would be the extra path? So it is the refractive index of that medium -1 times T. Okay, refractive index of medium -1 times T, right? N is the refractive index. Okay, what is refractive index? It's speed of light in vacuum divided by speed of light in that medium. Okay, so that is the extra path difference. And then therefore what would be the shift in the interference pattern? So it will be this extra path difference times capital D by small d. Okay, extra path difference times capital D by small d would be the shift from the center in the interference pattern, right? This thing is clear. If there is any slightest of the doubt, let me clear it. So see, you have suppose this glass slab, okay? So wavelength here would be different, right? Wavelength here is different. So if it is a denser medium, then what would happen? Wavelength would decrease, okay? Suppose here in air, if you consider air, suppose there the wavelength is this much, and this medium has refractive index twice as much. So then the distance covered in air and this medium would be same. But what about the waves formed? Okay, in air, suppose one wave is formed in this medium. What will happen if refractive index is 2? That means wavelength is half. So 2 waves would be formed, right? So that will introduce some part difference. Okay, so number of light waves formed, okay, within some distance. So if it is a denser medium, then what will happen? More number of waves would be formed. Okay, so extra path or extra part difference comes from there. Okay, good. So how much is that extra part difference? It is n-1 times the thickness of that medium, and therefore shift in the fringe pattern would be equal to n-1 times this t, the thickness of that slab, times capital D by small d. Okay, so you need to remember this formula. After that, let's see some questions. So let us see this question. For Young's double slit experiment, 2 statements are given below. Okay, this is from the NEET 2023. Okay, for Young's double slit experiment, 2 statements are given below. If screen is moved away from the plane of slits, angular separation of fringes remains constant. Is this correct? Not correct? There is plane of slits, there is a screen is moved away. What will happen to the angular separation? Will it remain constant or not? It will remain constant, right? Okay, so see, formula for angular separation is lambda divided by small d only. It doesn't depend on this capital D, right? What happens if you move the screen away? Then this fringe width will increase, okay, as you move it away, and this capital D also increases linearly, okay, but the angular fringe width does not change. It is just lambda divided by small d, right? So this one is correct. Fringe width remains constant. Then if the monochromatic source is replaced by another monochromatic source of larger wavelength, the angular separation of fringes decreases. Okay, so is this one correct? Yes or no? So angular separation theta is equal to, we know, lambda divided by small d. So if monochromatic source is replaced by another monochromatic source of larger wavelength, then angular separation should increase actually, because theta is directly proportional to lambda. If lambda increases, theta also increases. Okay, so this is incorrect. So what's the answer? Statement 1 is true, but statement 2 is false. This is the answer. Okay, this is clear. Very simple question. Okay, good. Let's see next one. This is not from NEET, some other exam. It's RS something, maybe Rajasthan, I don't know. Let's see. If the screen is moved away from the plane of slits in Young's double slit experiment, screen is moved away, then the linear separation of the fringes decreases, angular separation of the fringes decreases, angular separation of the fringes increases or decreases, linear separation of the fringes increases. Tell me. Option D? Yeah, correct. What is the separation? What is the value of beta? Very good. Lambda capital D by small d. If screen is moved away, then beta will increase. right? If d is increased, beta will also increase. So option D is correct. The linear separation of fringes will increase. All right, let's see next one. This is from NEET 2022. In a Young's double slit experiment, a student observes 8 fringes in a certain segment of screen where monochromatic light of 600 nanometer wavelength is used. Okay, 600 nanometer. Then in certain segment of the screen, 8 fringes are observed, right? If the wavelength of light is changed to 400 nanometers, then the number of fringes he would observe in the same region of the screen is. This is the question. Okay, so you have screen. Let's suppose distance of the point. So suppose this is the screen, this is the midpoint of screen, and this is some region of screen. So distance of this point from the center is suppose x, where for first kind of light, that is 600 nanometer wavelength, how many fringes are formed? 8 fringes are formed. Okay, then how many fringes will be formed for the second light having wavelength equal to 400 nanometers? This is the question. Tell me. Option C, it might be correct. Okay, let's check. So see, how can we write the distance? So suppose there are 8 fringes, no? That means it is 8th bright fringe. So we can write it as 8 times. So suppose it is nth bright fringe, we can say it is n times lambda capital D by small d. Okay. Now distance is same, number of fringes might be different, wavelength is different, and this capital D and small d is a constant. So for this fixed distance, we can say n times lambda is a constant. So I can say n1 lambda 1 must be equal to n2 lambda 2, right? Because d and small d, these are constants. Okay, and therefore you want what? You want n2. N2 is just equal to n1 lambda 1 divided by lambda 2. Just put the values. So n1 is 8, lambda 1 is 600 nanometers, and other one is also in nanometers, it's 400 nanometers. So don't need to change units, right? So then we get 6 by 4. Okay, you can divide this 8 by 4. So that's 2. 2 times 6 is 12. Correct. So it's option C. Okay, so this is very simple, right? Okay, good. Let's see next one. Which one of the following phenomena is not explained by Huygens construction of wavefront? Okay, so actually you need to just remember this, that Huygens could explain reflection, refraction, diffraction is the phenomenon that we are going to see next. Okay, he could explain interference. Okay, so Newton explained reflection, refraction, rectilinear propagation. Okay, Huygens theory could explains this thing, reflection, refraction, refraction. Okay, then next is interference, diffraction or diffraction, I don't know what do you call it. Okay, diffraction. Then there is one more thing called as polarization. So whatever phenomenon are related with wave nature of light could be explained by Huygens theory. Okay, but it can't explain origin of spectra. So there is another theory for that. So what is the spectra? So you might have seen in chemistry, okay, in physics or chemistry, that what happens if some substance or any gas is heated, it emits certain kind of light. So that is called as spectra, emission spectra. Okay. So how is that light emitted? So according to Bohr's theory, when an electron from higher orbit jumps to the lower orbit, it emits light which is equal to the energy difference between these two orbits. Okay. So when this electron jumps from here to here, it emits a light. Okay. And we'll see that. So energy of this light is equal to h times nu. H is a Planck's constant, nu is the frequency, and this is one particle of light, one packet of light. Okay, so called as photon. This is called as photon. So again there are, see, Newton, this is an interesting story. Newton said that light is made up of corpuscles, means particles. Okay, then came Huygens, he said that no, it's made up of waves. Okay, he could explain more phenomenon compared to that of Newton, right? Then came Young's, who proved with experiment that it is made up of these, it is made up of waves, but we didn't know what kind of waves. Then came Michael Faraday. Okay, so we'll talk about Michael Faraday and Maxwell. So Michael Faraday, he did some experiments, lots of experiments, and from those experiments he got a hint that light is made up of electromagnetic waves. So waves made up of electric field and magnetic field. Then came Maxwell and he proved it mathematically. Whatever is Faraday's theory, he proved it mathematically, and he also found the equations for the electromagnetic waves, and he also found that if electromagnetic waves travel in space, their speed would be equal to 3 into 10 raised to 8 meters per second, which is speed of light. Okay, so it proved that light is made up of what? Electromagnetic waves. Okay, but there are different sort of electromagnetic waves. Okay, different types of electromagnetic waves, and a part of that is visible light. Okay, but then after that some phenomenon were discovered which couldn't be explained by this wave theory of light. We didn't know which kind of waves, so that was also established, that electromagnetic waves. Okay, so that we are going to see in the next chapter, what phenomenon. Okay, so one is photoelectric effect. Okay, so then Einstein came and he said that no, light is made up of kind of particles, packets of energy called as photons. Okay, so before Einstein, actually there was Max Planck, who used this theory to explain the black body radiations. Okay, so now black body and these things, they are removed from our syllabus, but anyways, so again, so this is a full circle. Started with what? Particle theory, and again we came back to the particle theory, but we don't believe in particle theory now. We believe in what? The dual nature. Okay, so it depends on the experiment. It depends on which experiments are you performing. Okay, so which nature of light can be seen depends on which kind of experiment you perform. Okay, so the origin of spectra, these are spectra. The light emitted by an excited atom is called a spectra. It can be explained by photon nature of light, which is not wave nature, it's a particle nature. So this is the answer. It cannot be explained. This thing is clear? Yes, no? Okay, good. All right, let's see next one. The frequency of a light wave in a material is 2 multiplied by 10 raised to 14 hertz, and its wavelength is 5000 angstrom unit. The refractive index of the material will be. Okay, so refractive index is what? Refractive index is just C divided by V, speed of light in vacuum divided by speed of light in a medium, and we know that V is equal to what? Frequency is given, wavelength is given, so V is equal to n times lambda. Okay, but this n and that n are different. So let's say f times lambda or nu times lambda. Frequency is nu. Okay, nu is the frequency of light, and C is 3 into 10 raised to 8. So substitute values, 3 into 10 raised to 8 divided by nu is 2 multiplied by 10 raised to 14. Okay, multiplied by, you have 5000 angstrom units. So that is 1 angstrom is 10 raised to minus 10 meters. Okay, so then what do we get is 1.5. This is 10 raised to 14 minus 10 is 10 raised to 4, 10 raised to 4, and this thing is 10 raised to what? 3. So 10 raised to 4 plus 3 is 10 raised to 7. 5 times 2 is 10 again. So this all is 10 raised to 8. No, so this all gets cancelled out. What remains is 3. So refractive index is 3. Very, very simple question, right? Okay, let's see next one. The interference pattern is obtained with two coherent light sources of intensity ratio n. In the interference pattern, the ratio of this thing Imax minus I mean divided by Imax plus I mean will be. So let's find it out. So these are two coherent sources and their intensity ratio is n. Okay, so we can say I1 is equal to n times of I2, right? Because intensity ratio I1 is to I2 is equal to n. This is given. So then just use the formula. What is Imax? I1 plus I2 plus 2 times root of I1 I2. What is I mean? I1 plus I2 minus 2 times square root of I1 I2. Okay, what would be Imax minus I mean? So if you subtract them, then this thing will get cancelled out and it will be 2 plus 2 means 4 times root of I1 I2. Okay, so therefore you have Imax minus I mean divided by Imax plus I mean is equal to, it's equal to what? It's equal to 2 times square root of, it will be 4 times, right? 4 times square root of I1 I2 divided by, now if you add it up, this thing will get cancelled out. So it is I1 plus I1, 2I1 plus 2I2. Okay, so 2 times of I1 plus I2, right? Then you substitute I1 is equal to what? It's n times of I2. Just substitute that. Then what do we get? We get 4 times of root of I1 is n times of I2 times I2. Okay, divided by 2 times of this is, okay, 4 by 2 is 2, right? So 2, and in denominator you have I1 which is n times of I2 plus I2. So here we can take I2 common. Numerator we have I2 square root of that is I2 gets cancelled. So what remains is 2 times root n, and in denominator if you take I2 common, it is n plus 1. So the answer is 2 times of root n divided by n plus 1. So that is option B, right? This is clear? Okay, good. Let's see next one. Ratio of intensities of two waves are given by 4:1. Then the ratio of amplitudes of two waves is, okay, so we know, yeah, tell me. Intensity is directly proportional to amplitude square. Okay, so I is equal to some constant c times a square. What would be I1 is to I2? It is just a1 by a2 square, and this is given to be equal to, yeah, it's option A, right? That's correct. Okay, so this is given to be equal to what? 4:1, right? So this is equal to 4:1, and therefore A1 by A2 would be just equal to 2:1. Okay, very simple. All right, let's see next one. Interference is possible in light waves only, sound waves only, both light and sound waves, neither light nor sound waves. Tell me. Light waves only, right? Okay, so this is not applicable to light waves only, it is applicable to all kinds of waves. Light waves, water waves, sound waves, all kinds of waves. Okay. All right, good. Let's see next one. In a double slit experiment, when light of wavelength 400 nanometer was used, the angular width of first minima formed on the screen placed 1 meter away was found to be 0.2 degrees. Okay, so theta is equal to 0.2 degrees. What will be the angular width of the first minima if the entire apparatus is immersed in water? Right, so this is very simple. We know theta is equal to what? It's lambda by d. So theta is just directly proportional to lambda. Okay, and it's given that refractive index of water is 4/3. Okay, so refractive index of water is 4/3. So mu w, we can say it's equal to what? Lambda in air divided by lambda in water. Okay, so what would be lambda in water? It would be just equal to, or lambda in air we can say is equal to lambda in water times mu w. Okay, so we want theta in water, right? Theta is directly proportional to lambda, and that's why theta in water divided by theta in air just equal to wavelength in water divided by wavelength in air, and wavelength in water is just wavelength in air is just wavelength in water times mu. Okay, refractive index of water. So this thing gets cancelled out. And what is refractive index? Refractive index is equal to what? 4/3. Okay, so 4/3 in denominator means 3/4. Okay, so this is theta of w divided by theta of air. No, theta of air on other side. So we get 3/4. Okay, theta in air on other side. So what is theta? 0.2. 0.2 multiplied by 3/4. 3/4 is 0.75. 0.75 times 0.2 is 0.15. Right, so the answer would be 0.15. In Young's double slit experiment, if there is no initial phase difference between the light from two slits, a point on the screen corresponding to fifth minimum part has a part difference. Tell me. So delta x is equal to, tell me, 2n minus 1 lambda by 2. Okay. For nth minima, delta x is just equal to 2n minus 1 lambda by 2. So what is n? N is 5. 2 times of 5 minus 1 lambda by 2 means 9 lambda by 2. That's very simple. Right? Okay, there is nothing in this question. We just need to remember the conditions for constructive and destructive interference. Okay, conditions for the part difference, conditions for phase difference. Okay, let's see next one. In Young's double slit experiment, the separation between two slits is 2 mm. The wavelength lambda of the light used is 5896 angstrom unit. Okay. Distance d between the screen and slits is 100 centimeters. Okay. So capital D is equal to 100 centimeters. It is found that angular width of fringes is 0.2. Theta is equal to 0.2 degrees. To increase the fringe angular width to 0.21 degrees with same lambda and d, the separation between slits needs to be changed to. So this is very simple, right? Lambda is kept equal, d is kept equal, so it doesn't matter what is lambda and capital D. What matters is small d only, because they are asking the separation between slits needs to be changed to. Okay, tell me. So initial d is 2 mm. Okay, what would be d prime? So we know that theta is equal to what? Lambda by d, small d. Okay. So theta prime by theta would be equal to, see, this is inversely proportional, so it will be equal to what? D by d prime. Okay, theta prime is the changed fringe width, angular fringe width, and d prime is changed change separation between slits. Okay, put the values. So we want d prime, no? All right, let's put other values. So theta prime is equal to 0.21. 0.21 divided by 0.2 is equal to d is what? D is 2 and we want d prime. Okay, so then 0.21 divided by 0.2. Let's move this d prime on other side. So we get 2 times 0.2 divided by 0.21. Okay, or 20 by 21. 20 divided by 21 would be equal to 0.9 something, right? So this thing times 2, or if you have 40 divided by 21, how much is it? Tell me. 1 point, it will be 1.9 or 1.8. 1.9. Okay, so that's the answer, right? 1.9 mm. So very simple, right? Most of the questions are very simple. Okay, let's see next one. Young's double slit experiment is first performed in air and then in the medium other than air. Okay, Young's double slit experiment is first performed in air and then in the medium other than air. It is found that 8th bright fringe in the medium lies where 5th dark fringe lies in air. Okay, so medium is M, suppose, let's say M for medium. So 8th bright fringe in the medium lies where 5th dark fringe lies in the air. The refractive index of the medium is nearly. Okay, so this is also similar to the other question that we saw. This one here, it was N1 bright fringes for the wavelength lambda 1, okay, which corresponds to N2 bright fringes for the second wavelength. But now we have 8th bright fringe. So let's say N1, because see, the distance of that point from the center would be equal in both cases, right? Distance of this point from the center would be equal. Okay, so N1 bright fringes means N1 times lambda 1, okay, times capital D by small d. This is the distance, this is formula for distance. So this must be equal to what? 2 times n2 minus 1 lambda capital D by 2d. Okay, so distance of n1 bright fringes is equal to distance of n2 dark fringes. Okay, but the wavelength will change, right? This thing is clear. Distance of n1 bright fringes from the center, okay, it's equal to distance of n2 dark fringes in some other medium. Therefore wavelength is changing, right? And in place of n1 bright fringes we are having n2 dark fringes. So condition for dark fringes is, or distance of nth dark fringe is equal to 2n minus 1 lambda capital D by 2d, and that's why we are using this formula for the medium. Okay, so let's say 1 is air and 2 is the medium. No, it's 1 is the medium, right? Because it's given that 8th bright fringe in the medium, where 5th dark fringe. So 8 bright fringe in the medium, right? So first one is the medium and second one is air, because bright fringes are formed in the medium and dark are formed in the air. So then put the values. So 8 times lambda 1 must be equal to 2 times 5 minus 1 by 2 times lambda 2, right? Okay, so this dd will get cancelled, and what remains is, we want refractive index, no, take lambda 1 on that side, and this would be equal to what? 9 by 2. Okay, move this thing on this side. So 8 times 2 by 9 is equal to lambda 2 by lambda 1. Okay, the wavelength in air divided by wavelength in the medium. So this is equal to 16 by 9. 16 by 9 means how much? Tell me. It will be greater than 1.6, because 16 by 10 is 1.6. Dividing by 9 would be greater than that. 1.68 or this one 1.7, 1.77. So that's option C. Okay, this is clear? Yes, no? The intensity at the maximum in Young's double slit experiment is I naught. Okay, distance between two slits is d equals to 5 lambda. Lambda is the wavelength of light used in the experiment. What will be the intensity in front of one of the slits on the screen placed at distance d equal to 10 times d? So tell me. Okay, so see here, the question is like this. Suppose intensity as the maximum at the maxima is I naught, right? Intensity at the maximum in Young's double slit experiment is I naught. Okay, then distance between two slits d is equal to 5 times lambda, where lambda is the wavelength. And then what would be the intensity in front of one of the slits? So we want intensity in front of this slit, suppose one of the slits. If d is equal to 10d. Okay, so let's find out what would be the part difference over there. Okay, so what's the formula for the part difference? S2p minus S1p. What was that? X small d by capital D, no? That's the formula. S2p minus S1p, yes. X times small d by capital D. Okay. All right, so we know this, that delta x is equal to x times small d by capital D. Okay, S2p minus S1p, the part difference. Okay, S2p minus S1p is equal to x times small d by capital D. Right. Now, what is x? What is the distance of this point from the center? It's equal to d by 2. Okay, because separation between two slits is equal to d. Then, if you take any point, okay, any point means out of these two, any point in front of any of the slits. Okay, so its distance from the center would be equal to d by 2, right? So x is equal to, this x is equal to d by 2. Okay, so put d by 2 here. So you have delta x is equal to d by 2 times d divided by, what is this thing? Capital D is equal to 10d. So put that. So then this d gets cancelled. You have d by 2 times 10 means d by 20. So this is the part difference. And what is d? So it's given that d is equal to 5 lambda. So this is equal to 5 lambda divided by 20. So then you have part difference equals to lambda by 4. So part difference is equal to lambda by 4. What would be the intensity there? Okay, maximum intensity I max is equal to I naught. This is given, right? I max is equal to I naught. So if part difference is equal to lambda by 4, delta x is equal to lambda by 4, corresponds to theta equals to what? Phase difference equals to what? Phase difference is, let's say, phi equals to, so we know phase difference is 2 pi delta x by lambda. Okay, we studied this in last chapter. Okay, this is the relation between part difference and phase difference. So put that. So you get 2 pi multiplied by lambda by 4. Okay, this is lambda by 4 by lambda. So this thing gets cancelled out. 2 pi divided by 4 means what? Pi by 2. So it's equal to pi by 2. Okay, so I max is I naught, and I for this point would be equal to what? So we know it is 2i multiplied by 1 plus cos of phi. Right? What is this thing? Phi is equal to pi by 2. This is 90 degrees. Cos 90 is 0. So this is 2i. What is the maximum intensity? They are calling it as I naught. But if intensities of two interfering waves is equal to I, then we know that maximum intensity would be equal to 4i. And intensity of this point comes out to be equal to 2i. So what's the relation? This is equal to half of the I max. Right? This is equal to half of I max. That is half of I naught. This thing is clear? Yes, no? Okay. All right, good. So the answer is I naught divided by 2. Right? There is no confusion, no? Because here I have written I naught, then 4i, then this is 2i. Is there a confusion? No, right? Okay, good. All right. So see, here in this kind of question, what will you do? First of all, find out the part difference. Okay. And you can briefly remember it this way, that part difference of lambda means phase difference of 2 pi. If part difference is lambda by 4 means phase difference would be what? 2 pi by 4. Right? Part difference of lambda corresponds to phase difference of 2 pi. Part difference of lambda by 4 would be phase difference of what? 2 pi by 4. That means pi by 2. Okay. So if phase difference is given in terms of, sorry, part difference is given in terms of lambda, lambda by 4, lambda by 8. What will you do? Whatever is that factor, just divide 2 pi with that factor. Okay, if part difference is lambda by 8, phase difference would be equal to 2 pi by 8. So quickly find it out that way. Okay, and then make use of this formula, right? Okay, good. So let's see next one. Two slits in Young's experiment have widths in the ratio of 1:25. The ratio of intensity at maxima and minima in the interference pattern Imax by Imean is. Okay, so there is one more thing that you need to remember, that intensity is directly proportional to the width of the slit. Okay, intensity is directly proportional to width of the slit, right? So how? Because see, width is more means, suppose ideally they should be point sources. Okay, ideally the two sources in Young's double slit experiment, they have to be point sources. Okay, or very narrow slit, it should be very narrow slit. But then you can imagine it this way. So if width is increased, width is more, so width of this one is twice as much, then the number of sources over there would also increase. Okay, this is clear? Yes, no? And therefore number of sources has become twice, means intensity will also become twice. Okay, you can think of it this way, because now we are not going into photon picture. Otherwise it's very simple to understand. Width is twice means the number of photons that are coming out would be equal to twice. Okay, so here you can think of it in this way. So here suppose in a particular width, suppose one bulb fits, width is made twice, the two bulbs will fit. Okay, in a particular width, one bulb fits, then width is made twice, two bulbs will fit, right? And therefore intensity will become twice. This is clear? Yes, no? Okay, is this okay? Good. So therefore the width is in the ratio of 1:25. The ratio of intensity at the maxima and minima will be, what will be maxima intensity divided by minima intensity. So you know what is Imax and Imean. Okay, so I1 is to I2, this is given that I2, or let's take I1 equals to 25 times of I2, right? So then what do you get? So Imax by Imean, I will get rid of this thing. So Imax by Imean would be equal to what? Just equal to I1 plus I2 plus 2 times of root of I1 I2, and this thing is I1 plus I2 minus 2 times root of I1 I2. Just put values. So I1 is 25 times I2, so 25 I2 plus I2 plus 2 times root of, so this is 25 I2 times I2 means 25 I2 square, and in denominator you will have again 25 I2 plus I2, so that is 26 I2 minus 2 times root of 25 I2 square, so this is 5 I2. Okay, 26 minus 5, right? 26 minus this would be 10, no? 5 times 2 is 10, so that's 16 I2, and in numerator you will have 26 plus 10, so that would be 36. Is that correct? 36 is to 16. It's divisible, right? Divided by 4, it will be 9 is to 4. That's the answer. So option C, right? So this is simple. If you just remember this thing, that intensity is directly proportional to width, then there is nothing. All right, let's see next one. In the Young's double slit experiment, the intensity of light at a point on the screen where part difference is lambda is k. This is maximum intensity, right? For part difference of lambda, we have maximum intensity. So I max, and which would be equal to 4i, it's equal to k. You can write it this way. Okay, we know that I max would be equal to 4 times of intensity of one wave, right? The intensity at a point where part difference is lambda by 4. We just solved this. Tell me. It would be equal to k by 2, right? So resultant intensity here, where the part difference is lambda by 4, okay, part difference is lambda by 4, delta x is lambda by 4, means phase difference phi is equal to what? 2 pi delta x by lambda, and that is equal to, so 2 pi times delta x is lambda by 4 divided by lambda, so that gives pi by 2. We just solve this, no? Okay, so therefore what do we get? So resultant intensity would be equal to I plus I, or it's equal to 2i multiplied by 1 plus cos of phi, right? And cos of phi means cos of pi by 2, so that is 0, so it is 2i. So maximum intensity is 4i, okay, where the part difference is lambda, the intensity would be maximum, and they are calling it as k, but we know that is equal to 4i, and the point where the intensity, the point where the intensity, again I am saying intensity, the point where the part difference is lambda by 4, the intensity would be what? It's equal to 2i. So this is half. Okay, this is half of the maximum intensity, right? Okay, this is equal to k by 2. This is clear? Yes, no? Okay, good. Let's see next one. In Young's double slit experiment, the slits are 2 mm apart and are illuminated by photons of two wavelengths, means light of two different wavelengths. Lambda 1 is equal to 12,000 angstrom unit, lambda 2 is 10,000 angstrom unit. At what minimum distance from common central bright fringe on 2 meter on the screen 2 meter from the slits will a bright fringe from one interference pattern coincide with a bright fringe from the another? Okay, all right, so we just want to find out the distance where, at what minimum distance from a common central bright fringe, okay, on the screen 2 meter from the slits. So d is equal to 2 meters, this is given. Small d is equal to 2 mm. So bright fringe, first bright fringe, not first, some bright fringe of the first source coincides with some bright fringe of the second source, right? So bright fringes coincide means n1 lambda 1 must be equal to n2 lambda 2. So we need to find out that minimum n1 and n2, right? So n1 is to n2 would be equal to what? Lambda 2 is to lambda 1, and that is equal to, lambda 2 is 10,000 angstrom unit, lambda 1 is, okay, 12,000 angstrom unit. That is 10 is to 12 or 5 is to 6. So what does it mean? That the fifth bright fringe due to the first source will coincide with sixth bright fringe due to the second source. Okay, so fifth bright of first coincides is the spelling correct? I don't know. Coincides with sixth of the second, sixth bright of second. So we just found this, the fifth bright of the first coincides with sixth bright of the second, and then we want to find out distance of that point from the central fringe. So that is very simple. So let's find it for first one. So x would be equal to x of fifth bright for first would be equal to 5 times of lambda 1 to capital D by small d. Let's put the values. So it is 5 times of lambda 1 is 12,000. Okay, so 12,000 angstrom unit means 12,000 into 10 raised to minus 10. Capital D is 2, small d is 2 mm. Okay, so that is 2 into 10 raised to minus 3 in meters. So we just need to solve this. So this 2 will get cancelled. We have 12, 5s are 60. Okay, 10 raised to minus 3 in numerator will become 10 raised to plus 3, and this is 10 raised to minus 10. So it is 10 raised to minus 7. Minus 7 plus 3 is minus 4. So 60 into 10 raised to minus 4. So the answer is 60 multiplied by 10 raised to minus 4 meters, or 600, right, or 6 into 10 raised to minus 3 meters. So that is 6 mm. Okay, so the answer is 6 mm. This is clear, right? Okay, so again this is also simple, right? So almost all questions are like this. All right, let's see this one. This is recent one, NEET 2020. In Young's double slit experiment, if the separation between coherent sources is halved and the distance of screen from the coherent sources is doubled. Okay, the separation between slits is halved, so d prime is equal to d by 2, and separation of the screen from the sources is doubled. So d prime, capital D prime, is equal to 2 times of d. Then the fringe width becomes, so very simple. So you know fringe width beta is equal to what? Lambda capital D by small d. So beta prime, therefore beta prime would be equal to what? Lambda times d prime by 2 d prime, 2 small d prime. Oh, by 2, sorry, lambda capital D prime by small d prime. Okay, so put the values here. So this is 2d divided by d by 2, and then move that 2 in the numerator. So it becomes 4 times of lambda capital D by d, that is 4 times of original beta. Okay, beta prime is 4 times of original beta. So that's very simple. Okay, this is clear. Right, good. Then let's see next one. In Young's double slit experiment, the distance between the slits and screen is doubled. The separation between slits is reduced to half. As a result, the fringe width. So this is from Karnataka NEET 2013. This is from NEET 2020. So NEET adopted it from Karnataka NEET, right? 2013. So the answer is what? 4 times. The answer is 4 times. Okay, so that doesn't mean that this is original question, right? Because question is very simple. It might have come in different exams several times. Okay, let's see next one. Interference was observed in the interference chamber where the air was present. Now the chamber is evacuated. evacuated. If the same light is used, careful observer will see. Tell me, no interference? Interference with brighter bands, interference with dark bands, interference with larger width. Tell me. Okay, see, air is removed. Suppose interference pattern is observed in a room, and all of the air from that room is removed. All of the air from the room is removed. Then what will happen? There is a vacuum. Okay, so beta is equal to, lambda capital D by small d. Okay, and what about wavelength in vacuum compared to wavelength in air? So speed of light is maximum in vacuum, no? So wavelength in vacuum would be greater compared to that of wavelength in air, and therefore the beta in vacuum is also greater than beta in air, right? So interference will have larger width. Okay, larger width meaning the larger fringe width. This thing is clear. It's very simple, right? Okay, good. Then we have similar questions. So let's see this one, and other questions, 3-4 questions I will leave it for you. Okay, so if yellow light emitted by sodium lamp in Young's double slit experiment is replaced by monochromatic blue light of the same intensity, fringe width will increase, fringe width will decrease, fringe width will increase, fringe width will remain unchanged, fringe width becomes less intense. Tell me. So you have fringe width directly proportional to lambda. It is lambda capital D by small d. Option A, it will decrease. Yellow light is emitted by a sodium lamp. Okay, decrease is replaced by monochromatic blue light. You have this pattern Vibgyor, right? In this one, wavelength of red is maximum and this is minimum, and this yellow. Yeah, so wavelength is decreasing, no? That's correct. Wavelength decreases, so fringe width will decrease. Correct. So it is option A. So since wavelength of blue is less than wavelength of yellow, fringe width would decrease. Okay. All right. So this is more than 8:35. Let's stop here. Okay. Tomorrow we'll see the next part of chapter. I'm leaving 3-4 questions for you and also sending the homework problems. Please try. Okay. All right. Let's stop here. Have a good day. Bye.